Hello PreCalculus kids. Today we're going to look at some examples from section 11.5. We're going to do this one a little differently than some of the stuff we've done in the past with using the Flip Math site. So there's just going to be this one example video for this whole section. I'll explain more about changing this up a little bit. I'm trying to keep it as easy as I can keep it so that that we can learn how to solve these trig equations but not have it be too crazy. So here's what we've got going on. You've got trig equations. You've been playing around with them the last few weeks with simplifying and changing tangent to sine over cosine and all those transitions that I showed you in those previous videos. But today we're going to actually, this was the whole reason why you were doing that, we're going to solve trig equations. And so you remember, like back in the day of regular algebra, we would have something like this. We would have, say we'd have 2x minus the square root of 3 equals 0, and I would say to you, solve that for x, and you would say, sure. You would move that square root of 3 to the other side, becomes positive, and then you would divide by the 2. And you would tell me, all right, x is the square root of 3 over 2, and I'd be like, you are awesome. And that is true. But this time we're going to have trig functions in this place instead of x's in the place. But guess what? You treat it exactly the same way you would treat any other equation when you go to solve it. So if we take that same concept and we look over here at number 1, you've got 2 sine of x minus the square root of 3 equals 0. And you say, all right, well, get the sine by itself. So the square root of 3 goes to the other side. 2 sine of x equals, it's negative there, we cross over, now it's positive. And then we're going to divide by 2. So we get the sine of x equals the square root of 3 over 2. And that's the same thing we had over here when it was just plain old algebra. So here's what the difference is. Now what you're going to do is figure out where is the sine equal to the square root of 3 over 2, and guess what's going to be of the utmost of help to you. And it would be back to this lovely chart with the unit circle that we had from previous sections. Now, I'm going to include this chart in the notes that you can download for this so that you don't have to go look for it again. So we want to know the square root of 3 over 2. Where does that happen in the sine function? And I can see it's 60 degrees or pi over 3. And so I go back to the directions because the directions are going to tell me what numbers I want to use. This one tells me that I want everything in degrees. So we said that it's at 60 degrees. That's where it equals the square root of 3 over 2. But I have to see if there's another place because most times there is. So sine column, square root of 3 over 2, 120. Anywhere else? There's negative ones but not positive ones. So 120 is my other final answer. And you just solved a trig equation. So you can see it's really not a whole lot different than what you were doing when you were solving regular equations. So let's try another one. I want to get the tangent by itself. I've got to get the trig function by itself. If I do that, I've got to, well, let's see, I'm going to move the 3 to the other side. Negative tangent squared x equals, when it comes over, now it's a negative 3. Multiply both sides by a negative 1. Tangent squared x equals a positive 3. Well, I don't want the squared function, I want what the tangent is. So in order to undo a square, I have to square root both sides. By square root of tangent squared, I get a tangent. When I take the square root, remember square rooty, he's a plus or minus. He's a two-timer. He's got plus or minus going on, and it's going to be the square root of 3. All right, so then I go to my chart. On my chart, I end up with, look at the tangent column. I want everywhere in degrees where the tangent is the square root of 3. So if I go over, that's going to be 60 degrees, 120 degrees, keep going, 240 degrees, and then if I keep going down, another one at 300 degrees. So I have 4 answers for this one, and you'll see that that's a common thing when you have plus or minus. So let me write them all down. Again, I'm using the degrees because that's what the direction said to use. So 60 degrees, 120 degrees, we said 240 and 300. All right, here comes another one. I want to find the cosine this time. So it's a cosine squared. I need to get it by itself. I'm going to move the 1 to the other side first. 4 cosine squared equals a positive 1. 1 comes over. Divide by 4. Cosine squared is 1/4. Oh, it's a square. I want the regular. So I've got a square rooty, two-timer. Cosine of x equals plus or minus the square root of 1 is 1. Square root of 4 is 2. So I've got all the places where the cosine is a plus or minus 1/2. Again, you're going back to your chart. Plus or minus 1/2, and the cosine is 60, 120, 240, 300. Do those numbers look familiar to you, right? They were the same answers you had back in the other one, even though it was a different trig function. So here we go, 60, 120, 240, and 300. All right, here's where things get a little bit different. Because this one you can see it's not just one trig function and numbers that I'm moving around like a normal equation would be. This time I've got two different trig functions involved, a sine, cosine, and a cosine. So now you have to think factoring to do this one. So sometimes you're going to have to factor these things to be able to make it work. So this is all one term, this is one term, and I need to see if they have anything in common. And I can see they both have a cosine. So what I'm going to do is factor out a cosine. And that brings me with a set of parentheses. This is not like AC method factoring. That's going to come in a few minutes. But for now, this is just what do they have in common. If I take the cosine away from this first term, that leaves me with a sine. If I take a cosine out of this, I'm left with a minus 3. Now check yourself out. FOIL that or distribute that back and see if you get what you started with. Cosine times sine is sine cosine, cosine sine. Cosine times negative 3 is a negative 3 cosine. So you distribute it back and you know you got the right stuff. Now, if you are, whatever you factored out gets set equal to 0, and whatever's in the parentheses gets set equal to 0. So you've got cosine of x equals 0. I have the sine of x minus 3 equals 0. Before I pull my chart over, I'm going to take this 3 and put it to the other side, solve it out. Sine of x equals 3. Now I'm going to hear Levi in the background. Levi's barking at the mailman. All right, so if I look at my chart, cosine of x equals 0. Cosine of x is 0 at 90 degrees and at 270 degrees. So I'm just looking where cosine is 0. I get two answers. X is 90 degrees. X is 270 degrees. And then I go to look where the sine is 3. So sine column, I'm looking for a 3, and guess what? It ain't there. And you're like, what? What's going on? And so the deal is, if you remember the sine graph from when we were graphing these things, the graph goes like this. The tallest point it hits is right here. Do you remember what that value was? It's a value of 1. They're trying to say, what is it? When's it ever going to hit 3? And you're like, that ain't ever going to happen because it only goes as high as 1. So sometimes when you get numbers like this that are beyond 1, you're going to have no solution for that part of the problem. So this part gives me no solution, but this part gives me two answers. All right, so that's a factoring one. Now we're going to change the directions just a little bit, try some more. This time the directions say, all right, now find the solutions where you are between 0 and 2 pi. All that does is change the column you look at on your chart. So now I'm using this set of answers instead of the degree set of answers. So the problems are done exactly the same way. The procedure's not changing. So if I look at the first one, I'm trying to get cosecant by itself. Square root of 3's got to go to the other side. Cosecant of x equals 2 divided by the square root of 3. And that might make you cringe just a little because look, you've got a square root in the bottom and you're like, I can't have that. The math police will take me away. And so I multiply by the square root of 3 over the square root of 3. Remember, it's called rationalizing. Fancy math word. And that gives me 2 square roots of 3 over the square root of 9, which is 3. Nothing cancels. This 3's inside, this guy's outside. That's what you got. So cosecant of x is 2 square roots of 3 over 3. You're going to go to your chart and see where that happens. Cosecant. 2 square roots of 3 over 3. Right here, but I'm using the pi numbers, the radian answers. So my answer is going to be pi over 3. Let me see if there's another spot as I come down the line here. And 2 pi over 3. All right, they're my two answers for this one. So I've got x equals pi over 3 and x equals 2 pi over 3. All right, number 6 is a little more tricky, kids, because look at, I've got a sine on one side, I've got a cosecant on the other side, and they're not alike. I can't factor anything out. So I'm kind of looking at this going, what on earth can I do? And this is where section 11.1, when we did all of those changing sines into 1 over cosecants and such, using the identities, that's what you needed to know in order to do a problem like this. So let's think about this. We said we never normally change a sine or cosine. So this is going to stay 2 sine of x. But this guy, cosecant, I'm allowed to change him into his reciprocal identity, 1 over sine. This is the whole reason you needed to learn that crazy section of 11.1. Now if I think about that, this one on the left is really over 1. I can cross multiply these. It's a single fraction with an equal sign in the middle. And so if I multiply them, cross multiply them, I get 2. Sine times sine is sine squared. X equals 1. All right, now this looks like the ones we've been doing all along. So I'm trying to get the sine by itself, so I'm going to divide by 2. Sine squared x equals 1 divided by 2. I don't want a square, I want just regular old sine. That means I've got a square rooty. Square rooty is going to give me, I'll come over here, the sine of x equals square root of sine is squared, gives me just a sine. I've got plus or minus because I did a square root. The square root of 1 is 1. The square root of 2 is the square root of 2. And here's another situation where the math police are going to take me away if I don't rationalize that. So I'm going to multiply the top and the bottom by the square root of 2. That's going to give me the sine of x equals plus or minus the square root of 2, 1 times the square root of 2. And the square root of 2 times the square root of 2 is the square root of 4. The square root of 4 is just a 2. So you'll see that you get plus or minus the square root of 2 over 2. I'm going to go to my chart, and I want to know where is the sine, the square root of 2 over 2, plus or minus. And I'm using the radian answers, so it's going to be pi over 4, keep going down, 3 pi over 4, 5 pi over 4, and if I keep going, 7 pi over 4. You'll see they all look very identical. It's not like you're going to have, you won't have answers like pi over 4 and then a pi over 3 in that same realm. They're not going to work that way. They're all going to have that same denominator going on. So we said it's pi over 4, we said it's 3 pi over 4, we said it's 5 pi over 4, and we said it's 7 pi over 4. All right, so there's one that's a little more difficult. You had to use your trig identities, especially those reciprocal ones, to be able to solve that one out. Number 7. 7 is back to, I've got a sine cubed, and a sine. Luckily, they're the same trig function. If they're the same trig function, then think factoring. This is another factoring one. So I'm going to take, this has 3 sines, this has 1 sine. I can only take out the smaller number. So I'm going to take the sine of x, factor that out. And if I take 1 from the 3 that I started with, I still have 2 left. Sine squared x. If I take this sine away, I'm left with just a 4. Then whatever you factor out gets set equal to 0. And whatever you got inside the parentheses gets set equal to 0. This side solved. This one I'm going to work on. Sine squared x equals 4, square rooty. Sine of x equals plus or minus the square root of 4, which is 2. All right, let's go to the chart. Sine of x is 0. Sine is 0. I'm using the radian ones at 0 or 2 pi. You can include the pi in that or not. So 0 or 2 pi. So I've got 2 answers for this. X equals 0. X equals 2 pi. Is there another spot? I didn't finish looking down the column. And there is at pi. So there you go. There's my third answer. This one has 3 answers. So 0, 2 pi, and pi. If I go to my chart and I look for where the sine is 2, I have no values where it's 2. So then I got to think back, does that make sense? Does it have an answer? And it goes back to my picture that was over here that we did. Remember, the highest it goes to is to 1 or negative 1. And this guy's asking me, where is it 2 or negative 2? And you say, that is not going to happen. So this part is a no solution part. So as soon as you see that it's not on your chart, you should be thinking about, well, geez, is that something that can even happen? All right, here comes the last one like this with factoring. We're going to change the directions in the next set. Last one with this particular set of directions going between 0 and 2 pi. This one I've got cosine and I've got cosine, but one of them's squared and one of them's not. So the first thing that you notice is you've got the same trig function, which is awesome. So this would be, if I were back in algebra, let me just pretend, this would be the same thing as x squared minus 3x plus 2, except x is cosines. So I know how to factor something like this using my rules for factoring from back in the day. I need two numbers that multiply to 2 and add to be a negative 3. So regular old factoring back in algebra would have said two numbers that add to 2, or multiply to 2 and add to negative 3 would be negative 2 and negative 1. Let's check it. FOIL it back. X squared minus x minus 2x gives me minus 3x. Minus 2 times minus 1 gives me positive 2. There you go. And so what you're going to do is, instead of calling them x's, remember we're really doing a trig function, it's really a cosine. So really this equates for me in this problem as being a cosine of x minus 2, that's this guy, and a cosine of x minus 1 equals 0. So you just factored that trig function just like you would have factored back in the day with regular algebra. All right, so if I take a look at this, I'm looking to see if the shadow, maybe hang on a second, we'll close it in. There we go. Got a glare on there. So if I take and solve this, it's going to be the cosine of x minus 2 equals 0, and the cosine of x minus 1 equals 0. And then I'm going to just solve it. So this one says the cosine of x, swing the 2 over. This one says the cosine of x, swing the 1 over. And then I go to my chart and I'm like, where's the cosine 2? Cosine column, nowhere. Then you think, does that make sense? Does it ever get to 2? Well, guess what? The cosine graph does the same thing the sine graph does. It's just shifted a little bit. But the highest it goes to is 1, and the lowest it goes to is negative 1. So is it ever going to be a 2? He may want to be a 2. He can't ever be a 2. And so this part gives me a no solution. But if I go to the second part where the cosine is 1, chart-wise, where's the cosine 1? And we know that it happens at 0 and at 2 pi. There is nowhere else that it hits a positive 1. They're my only two answers. And remember, I'm keeping it in pi language because that's what the directions said to do. So I have at 0 and at 2 pi. All right, we've got 2 to go. And the directions change again. So here's the story now. Now they're talking about what are all the solutions. And here's in theory what they're talking about. Remember how these, I'm just going to use the sine graph again. Sine graph goes like this. It keeps going and keeps going. When does it stop? And you say, never. So if I think about how many times it's going to hit, let's just even say positive 1. It hits positive 1 here, it hits positive 1 here, it hits positive 1 here. And how many times would it hit positive 1 if I kept on going? And you'd say a million times, because that's what the graph does. It keeps repeating that same pattern. So they want to know all the solutions for this. And it has to do with the period of the graph. If you remember when we were graphing the trig functions, when we looked at what the period was for how long it takes for it to make one complete picture of the graph, for the sine and cosine functions, it took a period of 2 pi. Remember it was that 2 pi divided by b thing? So if I'm looking at this, 2 pi, and we're going to do this, they want it in degrees. Well, what is degrees as 2 pi? What's 2 pi in degrees? And we know that that's 360 degrees. So I'm going to give you a little chart here to put at the top of the page that's going to be what you do when you see that they want all solutions. So if it is sine or its friend cosecant, or if it is cosine or his friend secant, you're going to write at the end, after you solve it, just like you solved the last 8 problems, all you need to do is put plus 360 degrees n, and I'll discuss why that is in just a second. And same thing with cosine, because the period of the graph is 360 degrees. But if you remember for the tangent and cotangent functions, they were a little thinner. So anytime you have a tangent or a cotangent problem asking you for all solutions, this one you're going to add on 180 degrees n, because the period of the tangent and cotangent graphs is pi or 180 degrees. All right, so if I'm looking at the sine or cosine graphs, secant or cosecant graphs, it's plus 360m, because to get from this place to get to the next time it equals it is 360 degrees. To get from this place to the next times it equals it, it's another 360 degrees. So every multiple of 360 degrees is when you get back to that place, because it's a periodic function that keeps repeating that same pattern over and over and over again. So to keep it simple, that's the theory behind it. But the deal is, if you have sine, cosecant, cosine, or secant, just toss a plus 360n after it. And if it's tangent or cotangent, you toss a plus 180n after it. So let's try a couple of this type. Now, the procedure for solving these doesn't change from what you did in the first 8 problems. We're doing exactly the same thing to start with. It's at the very end that you have to do this extra doodaddy. All right, so this one I'm going to solve for cosine. The 3 comes to the other side. 4 cosine squared x equals 3. And then I'm going to divide by 4. Cosine squared x equals 3 over 4. Then square rooty, I've got a square rooty. And that gives me the square root of cosine squared is cosine. Square root of 3, remember this is plus or minus because I took a square root. Square root of 3. Square root of 4 is 2. And I don't have to do any rationalizing because that one actually gave me a denominator that is not a radical. So I'm going to go to my handy dandy chart again, and I want to know where is the cosine plus or minus the square root of 3. Now also watch, you want to be in degrees. So now we're back to using the degree column. So square root of 3 over 2 plus or minus cosine. I have 30 degrees. I'm going to keep going. I have 150 degrees. I have 210 degrees. And I have 330 degrees. So I have several places this time where it actually equals this. So let me write them down. Here's my first one. We said was 30 degrees. Then we said it was 150. Then we said it's 210. And then we finished with 330. Now, here's where the extra thing comes in, because they want all solutions. This one is cosine. Cosine gets added with plus 360n. Here it is. Plus 360 degrees n. All of them get the same thing. All right, there you go. So that is how the all solutions work. The procedure is exactly the same as it would be for the other 8 that we did. It's just at the very end, you need to say, well, geez, it's going to repeat that same thing every 360 degrees. It hits it at 30 degrees, it's going to hit it again 360 degrees later. And every multiple of 360 degrees after that. That's what the n stands for. So 360 times 1, 360 times 2, 360 times 3. All of the multiples of 360 is where you're going to end up hitting that value one more time. All right, number 10. This one I have tangent squared and I have a tangent. That makes me think factoring. So I'm going to go off to the side and I'm going to think factoring with this one. So if I do that, tangent is my x, as if it were an x squared, minus 2x plus 1. Now I don't even have to AC method that. That one's pretty simple. Again, I need 2 numbers that multiply to 1 but add to be a negative 2. So that's going to give me an x minus 1 and another x minus 1. And so I'm going to apply that as if x were tangent. So here's what it's going to look like. I'm going to have a tangent of x minus 1, and I'm going to have another tangent of x minus 1. Turns out they're the same thing, right, when I solve them. I'll get tangent of x minus 1 equals 0, tangent of x minus 1 equals 0, tangent of x equals 1, tangent of x equals 1. So really I didn't have to do this whole second half because it's going to give me the same answers as the first half. So I'm going to go to my handy dandy chart and look and see where is the tangent 1. I want to know in degrees where that's going to happen. So tangent is 1 at 45 degrees. Keep going. Where else is it 1? It's negative 1, but we don't want that. We want positive 1. 225. So I've got 45 and 225. X equals 45 and 225. Same answers for this, so I really don't have to repeat them. Then I go up here. They want all possible answers. So tangent means I add a plus 180 on. Here it is, plus 180n. Any multiple of 180 degrees after that is where I'm going to find that same value. All right, so in order to keep this easy, as I started out the video saying I was going to keep this easy, you'll find that all of our answers are going to be found on this chart. And that's how we're going to try to keep it simple. But just for fun, just for kicks and giggles, let me tell you this. And this, just as so you know, and why you learned this stuff earlier. Say we had something like this. Say we had 4 sine of x equals 3. And I went and solved that. Sine of x equals 3/4. And you go, well, wait a minute, Wenner, that's not on the chart. And I say, yep, I know, it's not on the chart. You can have, if you're solving a trig function, values that are not on the chart. And back in the day, here's what you did with that. You did this back in section, I think it was 9.3. You took sine to the -1 and put 3/4 in your calculator, and you got out a reference angle. Remember that? 48.6 is what it comes out to be. You can check it in the calculator, but that's what it would be. Then you have to think about, where is the sign positive? What quadrants is the sign positive? Sign is positive in the first and second quadrants. Again, I gave you a chart that showed you that. So in the first quadrant, it equals the same as the reference angle. And in the second quadrant, it would equal 180 minus the reference angle. Some of this should kind of be looking familiar to you. And so I would get these two answers. I would get a 48.6 and a 131.4. So my point to tell you is that not all the time when you're solving trig equations are you going to get something that's on the chart. There are possibilities where it won't be. But to keep things simple for where we're at right now, we're going to keep everything being values that are on your chart. So if it's not on your chart, then it's either a no solution or you've done something wrong. So I showed you some examples of what that no solution looks like when the sine equals 2 or something like that, where it can't graph to be that. But realize that solving trig equations can take you into a place like this. Again, to keep it simple, we're going to keep things just on our chart. All right, so you can email me with any questions. I hope you're all doing well, and I miss you. Bye.